Hello, today I am going to talk about antenna arrays. Till now we have discussed about basic antenna configurations, which are dipole antenna, monopole antenna, slot antenna and loop antenna. Now all these antennas have a very small gain, relatively 2 dB, or it could be 3 to 4 dB depending upon the length of the say dipole antenna, or for monopole antenna it depends upon the size of the ground plane. For example, monopole antenna for infinite ground plane directivity is about 5 dB, whereas for smaller ground plane monopole directivity is only about 2 dB. So now also these antennas have a very broad beam, so they will be sending the radiation in all the directions. For many point to point communication we require antennas which are pointing towards a certain direction, and for that we can use arrays of these elements. So today we are going to discuss about various types of arrays. So we will start with the arrays of two isotropic sources. So where we will assume that there are two isotropic. As I mentioned earlier, there is no isotropic source as such, but for assumption we can use isotropic source which radiates equally in all the direction. So we will use the arrays of two isotropic sources and we will consider various cases. For example, they are fed with a certain amplitude and we will vary the phase, and we will see that how the radiation takes place in different direction. The next topic we will take is the principles of pattern multiplication, where we will take a real antenna example. In this case we will take a dipole antenna, and then we will see how dipole antennas can be used in an array form, and we apply the principle of pattern multiplication. After that we will talk about linear arrays of n elements, where n can be anything from 2 to 10, 20, 100, and to start with we will take a case that all these elements are fed with uniform amplitude, but their phases will vary. So for example, if all the elements are fed with the same phase, it will radiate in the broadside direction, which is perpendicular to the direction of the array. Then we will go to the next topic, that is ordinary end fire, and in this case the phases are changing. And then from ordinary end fire we will actually see that there is a problem, the directivity of that is not as good as we would expect, and also beam was broadened. So by using the concept of increased directivity end fire area, I have given a nickname of idea. An idea can change the life. Okay, so we will see that by using just slightly different phase difference we can increase the directivity of the antenna. And then we will look into scanning array, where by changing the phase element you can scan the beam in different directions. After that we will talk about non-uniform amplitude, and we will actually see why we need it. First of all, if you use a uniform amplitude, what we will see in the case of a uniform, first side lobe level is about 13.5 dB below, and we cannot get lower than that. So by using non-uniform amplitude we can reduce the side lobe level to 20 dB or even 30 dB. And after that we will take examples of planar array, in which we will talk about rectangular array, circular array, triangular array, hexagonal array and so on. So let us take an example of array of two isotropic point sources. So let us say we have two sources here, which is source 1 and 2. Both of these sources are isotropic element, and we want to find out what is the E field at point P. Now few assumptions we will do it here. First is we are actually going to a far away point, so we are going to calculate what is the far field radiation. So the condition over here is that far field distance is much greater than the d, which is the distance between the two elements. So now assuming that since the distance is very large, we can assume that the field over here will be relatively constant as far as the amplitude is concerned, but the phase will be different. So we can write total E field as E0 e to the power minus j beta r1, where r1 is the distance from source 1 and beta r2 from source 2. Now since r is much larger than d, we can use approximation, and that approximation is that r1 can be said approximately equal to r plus d by 2 cos phi, and r2 will be r minus. So just to look at here, this is r2 here, and r is the distance from the origin. So, r2 can be drawn over here, and this distance will be half of the total distance, which is d by 2. This angle is phi. So, we can say that d by 2 times cos phi will be this particular distance. So, r2 can be approximately written as r minus d by 2 cos phi, and r1 will be r plus d by 2 cos phi. And here we are just measuring angle theta if it is measured from the perpendicular axis. So, then we can say phi plus theta is equal to 90 degree. So, we can also write phi as 90 minus theta. So, now we substitute the value of r1 and r2 in this case in this equation here. So, that equation gets modified. What you can see here that r is constant. So, we can write e to the power minus j beta r outside, and the inside term will be corresponding to this term here, which will come e to the power minus j beta, and since there is a minus sign and another minus sign, this becomes plus. Now, here we are just denoting psi. So, psi is beta d cos phi, which is written over here, and what is beta? Beta is equal to 2 pi by lambda. In fact, many a times we write beta or k. So, both the symbols are acceptable. If you read different books, you will see they use different symbol. So, basically we can write now beta as 2 pi by lambda multiplied by it. So, this is the expression for psi. Instead of measuring angle phi from the axis of the antenna, if we do measure from perpendicular axis, then we can write in the form of sin theta. So, now when we write here e to the power minus j psi by 2 plus e to the power j psi by 2, this is very similar to writing something like e to the power minus jx plus e to the power jx, and that will be equivalent to 2 times cos psi by 2. So, we can replace this function by a very simple cos function, and now we can substitute the value of psi. So, this is the array factor for 2 elements which are from isotropic elements. So, now let us just see a case here. So, we have just noticed that E is equal to 2E0. Now, this is a constant factor. So, we can normalize this factor and say it is 1. So, we can write normalize E field as cos dr by 2, where dr is defined in terms of beta d, which is equivalent to 2 pi d by lambda. So, one can actually use this simple expression. So, let us just take an example where spacing is equal to lambda by 2. So, if we take spacing as lambda by 2, substitute the value over here, and using this gets simplified to cos pi by 2 cos phi. So, now here phi will actually vary from 0 to full 360 degree to calculate the overall radiation pattern. But we can just take a few quick numbers and try to estimate the radiation pattern. So, let us say if I take a case of phi equal to 0. Now, cos 0 is equal to 1. So, this inside the bracket will be pi by 2, cos pi by 2 is 0. So, E field will be 0. Now, for phi equal to 90, cos 90 will be equal to 0. So, cos 0 will be 1, and at angle 60 degree, cos 60 degree will be 1 by 2. So, this will be pi by 4, cos pi by 4 is equal to 1 by square root 2. So, based on just these information, we can do the plot. So, this is phi equal to 0, and along phi equal to 0, we can see field is 0. And now, this is increasing at phi equal to 60, this value is 1 by square root 2, and then it becomes maximum value, which is 1, and then it is getting repeated over here. Now, this one is just showing the radiation pattern in this plane, but there is a also pattern which is along that. This entire pattern will be rotated along this particular axis. So, what you are going to see that this lobe is here, and that lobe is completely rotated, and it will be full 360 degree. So, we can actually now mention that half power beam width in this particular plane is nothing but 60 degree. We can say that this is the half power point, 60 degrees from here. So, this is 30 plus 30, 60 degree. So, half power beam width is 60 degree in this plane, but half power beam width is 360 degree in the another plane. and these two half power beamwidth can be used to estimate the value of the directivity, and for that we have given you formula earlier, which is 4 pi by theta e theta h. So here in one plane theta e is nothing but 60 degree, which is equal to pi by 3, and in the other plane theta is equal to 2 pi. So from that you can calculate the directivity of the antenna. Now instead of taking the two dipoles which were symmetrical with respect to origin, we can actually take one antenna at the origin and we can take second antenna at a distance of d. Now it does not matter how you place it, E field should remain same, but let us just look at the derivation now. So for one which is at the origin, so far field will be nothing but e to the power minus j beta r. So there will be no r1, r1 is equal to r here, so that term corresponds to 1, and this distance is d. So now the term will be e to the power j psi. So this psi here you should remember that if the distance is d by 2, this will become psi by 2. If the distance later on, we will take example when it becomes 2d, then this expression will be 2 psi. So now this 1 plus e to the power j psi can be simplified. If we take e to the power j psi by 2 outside, what we are left with is the plus and minus half terms, and if you now write this whole thing, this is same as before, which is cos psi by 2. Of course there is a additional phase term, but the additional phase term is, really speaking, we are not concerned about when we are looking at a far field. See, we are concerned about the phase term only when you are trying to do vectorial sum of different element, but once you have done the vectorial sum, after that we are only interested in the magnitude of the whole system. So now by setting E0 equal to 1, we can write exactly the same expression as before. Of course there is a phase term which we are going to neglect, and this entire equation can be also looked into the graphical form. So 1 will be, that will be the horizontal here, and plus e to the power g psi, which will be somewhere here, and if we take the effective or the addition of these two vector component, and that will be maximum will be along the direction of psi by 2. So it does not matter whether we take antennas symmetrical to the origin or one antenna at origin or at some other place, radiation pattern amplitude will remain same. So now let us just take another case where the two antennas are of the same type, but they are fed with opposite phase. So that means now this antenna is fed with, let us say, amplitude A, then this is fed by minus A, which is 180 degree phase shift, and they are again symmetrical with respect to origin. So for the first element, the element will be, value will be e to the E0 plus j psi by 2, which is the distance here. Now the second component, since it has a negative amplitude, so we can say that E field has a negative term. So now we can combine these two. So instead of cos psi by 2, now the term will be sin psi by 2, and this can be further expanded. Psi we can put the value which is dr by 2 cos phi. Again let us take a case of for d equal to lambda by 2. Now the question comes all the time, why we take d equal to lambda by 2? We can always take d as lambda by 10 or lambda by 4 or lambda or 2 lambda or 3 lambda. Now actually speaking, when you take the spacing as lambda by 2, the mutual impedance between the two is actually close to 0. So that means this antenna can be individually optimized and another one can be individually optimized, and the impedance loading of this antenna to this will not be there. So basically what happens, if you excite one antenna, some field will be induced on the second antenna, and if the second antenna is excited, some field will get induced on the first antenna. So if we take a distance as lambda by 2, the impedance effect is almost negligible. That is why we take as lambda by 2. But later on we will see what happens if you change the spacing, what is the effect on the gain, radiation pattern, and so on. So right now we will take a special case of d equal to lambda by 2. We substitute this value over here, and we get the total pattern as sin pi by 2 cos phi. So let us try to plot again. So we will take again a few cases here. So let us take, we take phi equal to 0. So cos of 0 will be equal to 1. So this expression becomes pi by 2, sin pi by 2 is 1. When phi is equal to 90 degree, cos 90 will be 0. So sin of 0 will be 0. When phi is 60 degree, cos 60 will be half. This will become pi by 4. So sin pi by 4 is equal to 1 by square root 2. So if we now start plotting it over here, so along phi equal to 0, field is 1, so field is maximum. As we move along, field is decreasing, it becomes 1 by square root 2 here, and then it decreases to 0. And then this whole thing is repeated in 0 degree, 90 degree to full phi plane here. And now we can actually see the half power beamwidth in this case is equal to 120 degree. Now in the previous case we had seen half power beamwidth was 60 degree. Over here we see the half power beamwidth is 120 degree. So that made people think why we cannot improve it, and this thought process only led to the increased directivity end fire array, which we will see later on. So now let us just take a next example where the two antennas are fed with equal amplitude, but the phase difference is 90 degree. Here we are going to take two different cases of distance. First case we will take when the distance is lambda by 2, and since the phase difference is 90 degree, which is equal to pi by 2, so we can actually take 0 pi by 2, or we can take minus pi by 4 and plus pi by 4. So that is the value which has been put here. So by substituting the value of that phase difference, so that equation gets modified slightly, and this is the combined effect where we are putting pi by 4 plus the rest of the term. This term is same as what we had seen earlier when the phase difference was 0, just because of this additional 45 degree on one side we are getting the term. So again we normalize. So let us say 2E0 is normalized to 1. We are taking a case of d equal to lambda by 2. So we substitute the value. So this is the total field for these two antennas which are of equal amplitude but 90 degree phase difference. Again we do the same thing. So we put phi equal to 0, and then cos 0 will become 1. So this is pi by 2 plus pi by 4, that comes here, and then when phi is 60, cos 60 will be half. So that will become pi by 4 plus pi by 4 plus pi by 4 will be pi by 2, cos pi by 2 is 0, and that is how you fill the entire axis from 0 degree starting to 180 degree, and that will be repeated for 360 degree. See again now we start plotting this whole thing. So along 0 degree field is 1 by square root 2, which is now going to 0 at 60 degree, and then it increases to 1 by square root 2, and then it goes here at 120 degree it is maximum, then at 180 it becomes 1 by square root 2. So if you really see here in this particular half, the half power beamwidth is complete 180 degree, because it starts from 1 by square root 2 here, and then it goes to 1, then 1 by square root 2 goes to 1, and 1 by square root 2, and there is a back radiation here. However, this situation changes slightly if I, instead of taking lambda by 2 distance, if I take lambda by 4 distance. So if we put, instead of lambda by d equal to lambda by 2 over here, we put lambda by 4, this equation gets modified over here. And now if we substitute different values of phi, just to take one example, so if cos 0 we put here, so cos 0 is equal to 1, so this will be pi by 4 plus pi by 4 will be pi by 2, this value will be equal to 0, and then we can fill all the other rows here. So now coming to this one here, so if we start plotting, so this is 0 degree, and at 60 degree it is increasing, at over here it becomes 1 by square root 2, and the beam maxima is over here, and then it is coming back to this. Now if you look into here, that the back radiation is almost negligible. Now you can actually think about, so for example, if the antenna is put near the coastal area, so if you put a omnidirectional antenna at the near the coastal area, then it will be radiating lot of power in the sea or along the ocean, which is not really desired. But if we put two elements of equal amplitude with the lambda by 4 distance and pi by 4 phase difference, then we can actually realize a radiation pattern which is radiating only in the one side, and the backside radiation will be almost negligible. Of course, the same thing can also be obtained by using a reflector also, which will reflect the signal from the backside. So let us just take now the next case, which is the two isotropic sources of same amplitude with any arbitrary phase difference. So that any arbitrary phase difference is defined by delta here. So we can again do the derivation that this is minus delta by 2, this is plus delta by 2. So expression is similar, except that now psi is total will be including plus delta. So the expression is exactly same as before, which is cos psi by 2, except that now psi consists of the distance as well as consists of the phase, and by changing the value of the phase we can actually change the beam direction. As we had seen, if delta is equal to 0, beam maxima was on the broadside direction, and when delta was changed from 0 to let us say 90 degree, the beam maxima was 120 degree for length spacing equal to lambda by 2, and when delta was 180 degree, the beam maxima was along the end fire. So you can change the radiation from broadside to the end fire direction simply by changing the phase difference between the two elements. So now let us just take a real example where instead of taking isotropic elements, so we have taken two same dipole, and these are small short dipole, and these are kept in the horizontal direction, and for this horizontal direction they are fed with equal amplitude and equal phase. That is what means same. So we have two same antennas. Now these two antennas are actually kept horizontal, dipole is kept in the horizontal direction. So where will be the beam maxima? Beam maxima will be in the perpendicular direction. Recall what I mentioned when we were talking about a dipole antenna. So dipole antenna, if you see from the front side, you will actually see the maximum intensity, and as you move from the maximum towards the tip, you will see the minimum radiation. But in this case, dipole is not vertical, it is horizontal. So for horizontal, if you look at the dipole, you will see the maximum radiation in the broadside direction and minimum radiation in this particular direction, which is along the x axis. Now that is the dipole pattern. Now array factor, since these two amplitudes are same, phase is same, so array factor will be have a maximum in the broadside direction. So now the total pattern will be multiplication of these two pattern, and that is known as principle of pattern multiplication. So in the form of equation, we can say for the dipole we can write the equation. Now this is sin phi. It is important how phi is mentioned and how you are doing. So in this case, if you see, phi is measured from the x axis. So in this direction phi is equal to 0. So sin 0 will be equal to 0, and that gives the minimum radiation, and at phi equal to 90 degree, sin 90 will be 1, and that gives the maximum radiation here. The array factor as before is nothing but cos psi by 2. So what will be the total radiation pattern? It will be multiplication of these two. So that is the total field, and what is psi? Psi is over here, and since it is broadside, delta is equal to 0. So now we need to multiply these two. So if you just look at here, so this is 1 multiplied by 1 will be equal to 1. So let us say if this is 0.7 here, and let us say if this is also approximately 0.7, then 0.7 multiplied by 0.7 will be 0.49, which will make it much narrower. So in fact you can think in the lighter way that two fat people multiplied together will give rise to a slim person. So if we can apply this concept in the real life, we can actually solve the problem of obesity from the entire world, where two fat people multiplied together will lead to the narrow people or a thin person. Well, that does not happen in the human being, but over here the simple wires or dipoles here can multiply, and this is giving a narrow beam, and if the beam is narrow, naturally it will have a higher directivity. Now, it is important how you place the antenna. Instead of putting the antenna in the horizontal in this case, if we put the dipoles in the vertical orientation, which is right over here, which is a vertical. So, now even though the dipole is same, but we are now writing, instead of previous case we had written sin phi, but now it becomes cos phi. So, it is important that from where phi is measured. So, just look again here, this is the phi equal to 0 axis. So, cos 0 will be 1. So, that will give me maximum radiation here, and when phi is equal to 90 degree, that will give to 0. So, this is what is the dipole pattern, okay. But the array factor remains the same, because the two dipoles are fed with equal amplitude and equal phase. So, array factor is in the broadside direction. So, now if we multiply the two, what we get? We get kind of a butterfly pattern. Why? Let us see, this is 1 here, 1 multiplied by 0 will be 0 here. Over here this is 0, but this is 1. So, 1 multiplied by 0 will be again 0 here. So, in between along this here, this has a finite value, this also has a finite value. So, that gives me a maximum thing. But now suppose you just thought this as a dipole antenna and you are going to put the thing, but orientation is very, very important. So, if you just put horizontal, then the beam maxima will be this, but if you made a mistake of putting it vertical, and if you are trying to make the measurement in the broadside direction, you will actually get a 0 value, and that actually creates butterflies in your stomach. That is what is the pattern about. So, please ensure that how you place the antenna, what is the orientation of the antenna, and how do you feed the antenna. Of course, this vertical thing will be perfect case if you are designing an end fire array. If it was end fire array, then what happens? This is the dipole pattern which is maximum here. End fire array, then the array factor will be also maximum in this, and then what you will get? You will get narrower beam in this thing, that would means higher directivity in the end fire direction. So, it all depends upon what is the application you are looking at. So, now we can actually go through the next point, n isotropic point sources of equal amplitude and spacing. So, here what we have, there are n number of elements are there, and they are started with 1, 2, 3, 4, 5 and so on. We are starting from origin. So, that will be the first point here. Axis is same, this is phi equal to 0. So, this will be phi equal to 90 degree over here. So, we can actually now find out what is the total field at a far away point. So, it is relatively simple if you follow the principle which we did for 2 element, and since this is origin, so origin the distance will be r1, but r1 is equal to r. So, this will be 1. The next term will be e to the power j psi, then the second next will be 2 psi, because the distance is 2d, then 3d is the distance, so 3 psi and so on. Now, where psi is as before, so there is a no change. Now, we need to solve this particular equation. The easier way to solve this equation is that you multiply this entire equation with e to the power j psi. So, it is multiplied on both left side and right side. So, that is the term over here. Now, all we do it is we take the difference of these two, and if we take the difference of the two, this term will be left, which is 1, and the last term over here, all the other terms will get cancelled over here. So, this is the left side and that is the right side. From here we can find what is E, and that is given by this expression, and this expression now can be simplified to this in a very simple way. What you do? You take e to the power j n psi by 2 outside here, and from here e to the power j psi by 2 outside here, and then what is left is e to the power minus j n psi by 2 minus e to the power plus j n psi by 2, which is nothing but sin n psi by 2, and down below it will be sin psi by 2. So, this is the array factor, and what is the maximum value of this array factor? The maximum value is when psi is tending towards 0. because when psi is tending towards 0, see if you just look precisely 0, it will give you something different. Let us say sin 0 is 0 divided by sin psi by 2, that is 0. So 0 divided by 0 will be indeterminate, but you have to apply de Hospital rule, and that says when it is tending to 0, so sin x tending to 0 where x is small will be equal to x. So this term becomes x, and this n psi by 2, and down below is psi by 2. So the maximum value will be equal to n. So we can now write E normalize is nothing but sin n psi by 2 divided by this here. Now this is an important thing, and in the next lecture we will talk about more detail about this particular thing here. And remember, all the pattern, all the calculations can be derived from just this one very simple equation. Okay, I will just show you the plot, but we will continue in the next lecture. So this is the plot which has been plotted for n equal to 1, 2, 3, 4, 5 and 10, and you can actually see the number of side lobes here. So by using this equation we can find out what is the half power beam width, we can find out what is the direction of the null, we can find out in which direction there will be side lobe, what will be the amplitude of the side lobe. So in the next lecture we will do the larger array, and we will also see different cases. But just to summarize, so we started with the two isotropic elements which are fed with equal amplitude, different phases, and we also saw for 90-degree phase difference for two different cases, lambda by 4 and lambda by 2, and for lambda by 4 we could actually realize the radiation which is negligible in the back direction. And then we looked into the pattern multiplication and how the dipoles can be placed and how the radiation pattern cumulative can be obtained, and we just looked at the derivation of the n element. So please go through it, and in the next lecture we will talk about more about how to calculate directivity, how to calculate null positions and so on. Thank you.